Alright, everyone, so let's pick up where we left off before spring break. So, if you remember, we were on chapter 11, which was talking about how we select portfolios among the different choices that we have. And we covered the expected utility method using preference functions. Then we talked about risk tolerance functions. And now we're coming to safety first models. I did discuss the first criteria in safety models before, which is what we'll talk about today, Roy's criteria. But I thought I'd go over a review just so we're all back on the same track. So, what do first models assume? They assume that people are not going to be trying to do a lot of math to figure out which is their best portfolio, but they'd rather like to just minimize the risk of getting some bad outcomes. Okay, so the criteria will talk about how investors go about doing that, and the first one is the Roy's criteria. Okay, and Roy's criteria basically is talking about trying to minimize the probability of obtaining a return below some level. Okay, so it's, if you say it symbolically, it looks like this: trying to minimize the probability that our portfolio return falls below some minimum level that we've picked. Okay, so let's call that RL. Now, RL would be that return below which you do not want to fall. Then you do not want to get your portfolio falling below that level. If it does, we want to choose the portfolio that has the lowest probability of doing so. Okay, how do we test that? We assume a normal distribution. So, what does a normal distribution mean? It means it's that bell curve kind of a picture that we're used to seeing, where there's some mean and some standard deviation. And if we were trying to follow Roy's rule, we'd be trying to go furthest to the left as possible. Okay, so we're trying to go as far left as we can in order to minimize the probability of obtaining a return in that region. Okay, so let's assume, so basically what we'd say is that it would be where RL was the maximum number of standard deviations away from the mean of a normal distribution. Okay, where's the mean located in a normal distribution? Right in the middle. We call that mu, and we'll call the standard deviation sigma. Okay, but we are going to use our own symbols for them. So we'll go about doing that. Okay, so let's say 5% is the minimum return desired. Okay, so if 5% is the minimum return desired, our L would be 5. Okay, and then we have these numbers. Okay, we have these three different portfolios. We have portfolio A, portfolio B, portfolio C. Portfolio A has a mean return of 10 and a standard deviation of 5. Portfolio B is 14 and 4. Portfolio C is 17 and 8. And we're saying, hey, I'd like to get a 17% return, but I also see that the risk of that portfolio is pretty high. Okay, so which portfolio am I going to choose that will help minimize the probability of me obtaining a return below 5%? Okay, so we're going to try and calculate these three cells right here. How do we go about doing that? We follow the z-score formula. Okay, this z-score formula, which, what's a z-score? If you remember from your business stats class, the z-score is just where we subtract away the mean from some value and divide by the standard deviation of that distribution. Okay, so we are trying to convert all our portfolios to this normal distribution that has a mean of 0 and a standard deviation of 1, and try to find how many standard deviations away from the mean are we going to. Okay, so if we have all our numbers given, let's calculate these values for A, B, and C. So for A, the z value for A is going to be, we're just calculating RL minus RP bar divided by sigma P. What's RL? It's always 5. Minus RP bar. RP bar is the expected return of our portfolio. Expected return of my portfolio is 10. Divided by the standard deviation of my portfolio. Standard deviation is 5. And so ZA is minus 1. Okay, so 5 minus 10 is minus 5, divided by 5 is minus 1. Okay, so we are 1 standard deviation away from our mean. Okay, similarly, we calculate ZB. You don't have to call it a Z value, okay? It's just to tell you that we're still doing the exact same thing that we've done before. Okay, now for ZB, our RL is still 5. That hasn't changed. We do not want to go as far to the left. We do not want to go below 5%. but our expected return has changed. What's our expected return now? It's 14. So 5 minus 14 divided by this one has a standard deviation of 4. If you do that calculation, you're going to get minus 2.25 for B. Okay, so we're minus 2.25 standard deviations away from the mean for B. And if we do the same thing for C, we're going to have 5 minus, now our mean is 17, divided by 8, okay, which is our standard deviation. If you do that, you're going to get minus 1.5. Okay, so for C, we are minus 1.5 sigmas away. Okay, so if you plot that on your plot, basically on the normal distribution, for A, you're about 1 standard deviation away, so you're here. That is ZA. Okay, this is minus 1 sigma. Okay, for B, let's put another color just so you see that. For B, we're minus 2.25. Let's say it's somewhere over here. Okay, minus 2.25 sigma. And let's choose a third color for C. I don't know, any color, right? For C, let's say we're somewhere over here, and that's minus 1.5 sigma. Okay, sorry, that color choice was definitely not a great one. But anyway, so if our goal is to minimize the probability, we're trying to go as far left as we can. If we're trying to go as far left as we can, the one that's going to give that to us is portfolio B. Okay, portfolio B is the one that we're going to choose because that's as far left as we can. Let's try to make it into a box. Okay, that does not look like what I'm trying to do. Let me try one more time, just so that we can probably make a rectangle. There we go. So I'll move this down a little bit. Portfolio B is our choice, okay? Okay, so now let's think about it. If we do not want to deal with all these negatives and so on, we want to have some simple way to call Roy's rule. Now that I've explained to you what is our goal in this situation, our goal is to sort of pick that one. Okay, minimizing this ratio where we do the lower limit minus the expected value for a portfolio divided by the standard deviation is the same thing as if we just put a minus sign on the top and call it a maximization problem. Okay, we're trying to maintain the same format that we've been using in all the different chapters, where we've maximized the slope of the efficient frontier and so on in order to obtain the optimal portfolio. Okay, so we're trying to maintain that same format. If we do a minus sign to the top, we do a minus of what we have. So if we do, let's just write it over here, minus of RL minus RP bar divided by sigma P. If you do a minus of that, you're going to get a maximization problem now because we're flipping the sign. We still want to go the furthest out, but instead of RL minus RP bar, we're going to have RP bar minus RL over sigma P. All right, and now instead of minimizing, which is taking us farthest to the left, we're going to go farthest to the right with positive numbers. Okay, so basically what we can say is if the portfolios were equally desirable, okay, if all the portfolios had the same sort of choice, same probability of being chosen by us, that means that they'd all give us the same value for that ratio, right? They'd all give us the same value, and if it was the same value, we can call it any letter. Let's call it K. Okay, so Roy would say that if they were all the same, we're going to have an RP bar, which is our expected return of the portfolio, minus the lower limit divided by sigma P, which is a standard deviation, gives us some value K. Okay, now if we did not have all the same values K, we're trying to maximize this ratio, so we're going to pick the one that gives us the highest value of K. Okay, the highest value, because we're trying to maximize this ratio, right? And this ratio always ends up with some number K. Okay, like before, where we had minus 1.5, minus 1, minus 2.25. Okay, now they'll all be positive numbers because we just flipped the numbers. So we'd have 1, 1.5, and 2.25. And we're trying to maximize this K. So if our K was 2.25, we're going to pick that one. Okay, we're going to pick the portfolio with the highest K. Okay, based on Roy's criteria. Now, if you want to look at this in a graphical format, we can just rearrange this sort of ratio right here. we can bring the sigma p up to the top, so we'd get and take the RL over to the other side. So this equation now becomes this thing, okay? RP bar is equal to RL plus K times sigma p, okay? This looks like the equation of a straight line, okay? The straight line has an intercept of RL, a slope of K, okay? And this should sort of remind you again of our efficient frontier, right? The efficient frontier when riskless lending borrowing exists. So we're trying to maximize the slope of the function. If we have all these three different portfolio choices, we're gonna pick K3, okay, which is the portfolio with the highest slope. Okay, so this should not say K1. It should actually say K3, okay, because we want the highest, right? So that is basically Roy's portfolio. I'll end the video here with Roy's portfolio, with Roy's criteria, sorry, for portfolio choice, and then I'll create a new video for Karaoka's rule, Tausa's rule, and so on. Okay.